For number 38 here in section 3.3, we're asked to prove that if A is invertible, so is A inverse. So A invertible, so is A inverse. And then we want to show that the inverse of the inverse is in fact A. So this one could be a little strange perhaps to prove. That should be the word is. If you aren't used to doing proofs with matrices and whatnot and trying to figure out when you do have a proof, this will be in some ways similar to number 39. A lot of it turns out to be just maybe notation, at least it seems like that. So for instance, we know by definition, so A is invertible, so it has an inverse. Right, so what that means is A times its inverse is equal to the identity matrix, and its inverse times A is equal to the identity matrix as well. Right, so either one works. So A is invertible, we're guaranteed the existence of this sort of A inverse. In order to show that well, let me just highlight it, that this fella is also invertible. Well, if it's invertible, then we're asking, is there some matrix, maybe call it B? Does the matrix B exist so that both of these could be the identity matrix? If so, then this right here is invertible. So this is just a matrix. So this isn't a symbol. This denotes a special matrix for us. But we know this happens. We know this because, in fact, if I just stick in matrix A for both these B's, I know I will get the identity matrix. So, yes, because I can tell you exactly which one. I can tell you there is a matrix that we called A before, maybe we'll do it in a different color, that if I multiply A inverse by it, I get the identity matrix, and if I multiply it this way, I also get the identity matrix. And so this looks just kind of like I wrote the same thing twice, but what's given here is that A implies that A inverse exists, and we have this relationship. And because of the symmetry of this invertibility, we can also say, therefore, this new matrix here, that one also has an inverse, which was A in the first place. Now, so that's a proof of the existence, in that if A is invertible, so is A inverse. The next thing we wanted to prove was that the inverse of the inverse is A, and we kind of just proved that in a way, right? Because we just said, oh yeah, this is in fact what will undo it. But if you want to get some notation in there that makes sense, so thinking about, maybe let's say it this way. Recognize that this is just the name of a matrix. So if I wanted to, I can call it, give it another capital letter. So let's just say for a moment, I'm going to call this thing, I'm just going to say it's the same as matrix C, whatever you want to call it. So if I were to do that, I'm going to take this equation here, I'm going to rewrite it as C times A is equal to I, right? Just sort of renaming it so we don't get too caught up on the symbols. So if I were to solve this for A, I'd say, well, let's multiply both sides by C inverse. And what you need to be careful of here is when you multiply the left-hand side, notice how C inverse is multiplied on the left side, so I would also want to do that down below. So down here, do C inverse times I. On the left-hand side, C inverse times C gives you the identity matrix times A. And the right-hand side, that's really just C inverse. C inverse times identity is C inverse. But likewise, the identity times A is just A. So A is in fact equal to the inverse of C. But notice this, C was just a fancy name for us. C was just what we were calling A inverse. So I could just write it like so. And that's really sort of what the proof comes down to. And I even wrote it out with more steps than maybe you even need, but trying to sort of see how you can, if you can rearrange these things following the rules, then that can constitute a type of proof for us.